Hello everyone, and welcome to today's webinar entitled Solving the Multi-Application Challenge, Getting from CAD Model to 3D Print, sponsored by Spatial Corporation. I'm Jim Anderton, Director of Content here at engineering.com, and I'm looking forward to an interesting and informative hour. And just a reminder to attendees is that at the end of today's presentation, we will have a question and answer section. And for questions and answers, you will notice a console in front of you on your screen. Please pose your questions there, and I will field them at the end of the presentation. You know, speed from art to part is the goal of every designer in today's engineering environment. But getting there, well, that's often slowed by the need to use multiple separate applications to get from your CAD model to a 3D printed product. Now, in this webinar, Ray Bagley from Spatial Corporation will explore the rapidly evolving needs of additive manufacturing software applications. We're going to learn what defines the ideal software platform for OEMs and ISVs that will allow those same users to perform all the needed tasks in a single application. We'll learn how to avoid degradation of the design when moving from CAD to STL files. We'll also learn how to optimize the design for 3D printing through smart setup choices and how to take advantage of hybrid, additive, and subtractive technologies. Let me talk a bit about this afternoon's speaker. Our expert for this webinar is Ray Bagley. He's Product Management Director at Spatial. Now, Ray has more than 2 decades of experience in engineering software creation, but he's also a mechanical engineer by degree and at heart. Ray enjoys driving the software solutions that make advanced manufacturing technologies adoptable on a wide scale. Ray?
Thank you, Jim. Hello, everyone, and thanks for joining us today. So, as Jim mentioned in the introduction, we want to talk today about getting from a CAD model to a printed model. Whatever that printed technology is, whether it's in plastics or metals and the variety of things available. It seems simple, and there's been so much press in the last few years about this exploding market, but in truth, if you've been attempting to print parts yourself, you probably know that it's not as simple as it seems, or as it's made to sound like. So we're going to go into some of the details about what it takes to get from CAD model to print in a production environment. Before I dive in too much further, we'd like to get to know the audience a little bit and take a quick poll. Jim?
Thanks, Ray. Let's kick off the audience poll. Attendees will be able to choose from 5 options in front of you, and I encourage you to do so. And the initial poll is, which describes best what you do? Please select one of 3D printer manufacturer, service bureau, software application developer, a manufacturer that owns or uses a 3D printer in-house, or a student or individual involved in academic research. Again, please choose one of the options of 3D printer manufacturer, service bureau, software application developer, a manufacturer that owns or uses an in-house 3D printer, or student or researcher. These choices, of course, represent the entire spectrum of 3D printer users, individuals that are involved in additive technology. And we have results coming in. I will stand by for a few seconds while we allow results to stream in, and we will have in real time a graphical representation of the results, and they're still coming in. We'll just hang in for a few more seconds while those votes stream in, and they're streaming in as we stand now. And here are the results. Not surprisingly, perhaps, manufacturers with an in-house 3D printer, 38%, tied with students or academic researchers at 38% for this sort of top-ranking score, followed by software application developers. Ray, are these results sort of match your experience?
I think that's great. That's actually, I'm pleased to see that, because I think the people then on the poll or on the webinar will be able to relate to the challenges that I'm talking about.
That sounds great. Okay. And thank you, respondents. And there'll be a couple of other polls further along the presentation, right?
Great. So those of you who use the printer or are involved in actually trying to manufacture parts with this technology are probably familiar that getting from a CAD model to a printed part is not a one-step operation. You know, when this industry was called digital prototyping, people were pretty happy just to get a part in their hand that resembled the thing that they had designed, and they could maybe put it in a mock-up assembly. But now that we're manufacturing parts in production using these technologies, the expectations are entirely different. with the metal prints that can take 2 to 3 days and thousands of dollars of materials, you really need to be sure that the thing you're going to print is going to come out successfully before you hit the go button. The complete flow involves many different steps, and some people aren't even performing all of these steps yet today, but they will be in the future. So let's talk through some of those. The first is this axiom that everyone involved in computers is familiar with, and that's garbage in and garbage out. Spatial has been in the 3D data translation business for a very long time. In fact, we're the industry's leading provider of CAD translators to all the software applications that many of you are familiar with, even if you're not familiar with Spatial as the core developer of that technology. And something that we can say to be true without any argument is that when you're working with CAD data, the native proprietary files from the CAD systems are the most reliable source for that data. For example, a CATIA file or a SolidWorks file or something from NX. And those are the most reliable because the developers of those applications, these major companies, work very hard to ensure that that file format is 100% reliable for their application and their users to preserve access to their data for many years at a time. The next level of quality data comes into the standard formats. These are usually a step down in reliability from the native files, and they can vary in reliability. It really depends on how much care is taken by the developers of the application in writing the exporter. And there's always, almost always, some kind of translation or simplification of the data that happens when moving from the native format into these standard formats. But you can still get good, reliable data out of the standard formats depending on the author. Often, the data is not that good because the authoring is not so good. None of these formats are inherently deficient, but the quality of the authoring really varies quite a lot in the industry. And then the last is the tessellated formats. These are known as STL, is the most common used in this additive manufacturing market. There are others, and they're all just based on triangles that are connected to represent the outside of a part. STL is really not as good in terms of its ability to communicate 3D data as these more precise, or we call MCAD formats. And the reason is twofold. The first is that the format itself is extremely simple. It has the capacity to represent a very small amount of information. It can only have the triangles, not really how they're connected. It can't carry information like colors and materials and other information. And the second reason is that the quality of the writers that are out there seems to be all over the map. We see a tremendous amount of STL data that's of extremely poor quality. So much so it makes me scratch my head and think, what kind of application wrote this file that is this corrupted or missing this much data? So it's a little unfortunate that the additive manufacturing market has made itself reliant on STL as the key format. Now that's changing slowly. There are new formats coming out to replace it, but if our experience in traditional computer-aided manufacturing is any guide, it'll be quite some years before STL gets displaced by newer, better formats. The mature CAM market, computer-aided manufacturing, understands this need for quality very well and has been making the shift to using native CAD translators so that they know they can get the most reliable data, because that saves precious engineering and manufacturing time that's not spent trying to repair an imported model that came from poor quality data, or trying to reimagine or reinfer a design intent that was lost when the model was simplified for the export process. So that's the first major step, getting data into the application that you're going to manufacture. The next thing that has to happen is checking and healing that data. Now, if it's precise BREF data, if it's coming from a proprietary CAD system, we don't generally have to repair it. If it's coming from a standard format, very often that data has to be repaired or improved, and Spatial does that as part of our interop product. Now that we're dealing with this tessellated data as STL, I'm going to walk through some of the common pathologies and errors that we find in these files. The first is just missing data, missing triangles. If you have missing triangles, then you don't have a watertight solid volume. And that being a watertight solid volume is really the first requirement of all the slicing algorithms, be they from Spatial or someone else. So you have to fill in these holes where triangles are missing. Small holes like this are pretty simple to fill. I see a lot of data with just holes, complete surfaces missing from the part of this questionable STL data that's out in the wild. The next common error is we call flipped triangles. Triangles all have to be oriented the same way with the right-hand rule in order to be able to determine that you have a closed volume. And often we see files that don't comply with that. So you have to have algorithms understanding the geometry to identify and correct this and get all the triangles pointing outward so that you can create this watertight volume. Very often the basis for the STL file that gets generated out of a CAD system is the triangulation that was created for visualizing it. To put a 3D model onto the screen, you actually have to tessellate it into triangles. That's the language the graphics card speaks. So every CAD system has the ability to do that. And you can create triangles that look pretty good on the screen and may have flaws that the user can't see, and that's okay for visualization. But when you actually need to slice that to make a 3D print preparation, those kind of errors will disrupt the slicing and make it unreliable. So in this case, you've got bad connectivity from the triangles or a small triangle that's flipped over, maybe not noticeable when you're just visualizing the part, but it will create a problem when you try to manufacture from that data. This is another type of error that we have to repair in the STL before we can move on to the next steps in preparing for manufacturing. Another very common thing that we see is parts that look good at first. So for example, this model of the spark plug. Oh, it looks pretty nice. We look at the mesh, the tessellation. This looks pretty healthy. It doesn't have the problems of missing data or badly intersecting triangles. But then when we look further, we see it was actually modeled as an assembly. And so there's 3 or maybe 4 parts here in this assembly that all overlap. But if you slice that directly to print it, you're going to have problems, because at least at the boundary where the multiple parts intersect, you're going to get redundant laser paths or redundant machine paths. Now, if it's an SLM or SLS kind of process, then the laser is going to go over the same spot too many times, and it will change the metallurgy or change the behavior of the materials. If it's an FDM kind of process, well, now you're going to be trying to print 2 beads of material in the same place, and that's probably just going to make a mess on your printer and a mess of the part. So this is another way that the data that someone requested that this model be printed, but it's not ready to print yet. You need modeling, 3D modeling capability to resolve this assembly into a single part volume that's ready to be printed. And having those modeling tools is something that Spatial's been doing for decades, and people trying to develop their own applications will really struggle with these problems of how do you Boolean or otherwise resolve these different volumes into a single volume. And speaking of other modeling, there may be other modeling operations that you need to perform on the part, preparing it for the manufacturing. Every manufacturing engineer or manufacturing shop floor guy will tell you that the part he receives is never the one that's ready to be made. It's sort of an axiom in the great divide between manufacturing and design, and sometimes limited respect one has for the other. But in the case of additive, you may need to add some material and reduce the size of holes so that they can be finished machined to an accurate size, or tapped for threads. Or if you have hybrid processes, so some of the exciting new machines that can do additive and subtractive in the same machine, you have to segment the body to define those different processes. So for example, for this part, if this were going to be done as a hybrid, I need to print the first half of the part, then come back and perhaps finish machine the inside of those holes so I can get a nice smooth interior, then come back and print the top part of additively bring in material for the remainder of the part. Well, to define that process, you need to be able to split up the body into these separate parts that represent the different process stages. That again takes very strong, reliable 3D modeling tools. So now once we have the part basically designed as we think the part's ready to manufacture, well, you have to get it in the right orientation in the build volume. There are some, you may want to use automatic tools for this that would optimize the orientation of the part based on some parameters. Those parameters might be the volume of support material that you would need, or minimize the area of the downward facing surfaces, or minimize the number of support contacts on the part to reduce the post-processing. Those are just some ways that you might have an automated optimizing process. I've talked to quite a few users who say they would never trust automation and they will always do it manually because they're going to bring into that judgment what surface finish they want on different surfaces, right? The up-facing surfaces tend to have a smoother surface finish than down-facing surfaces. Well, there's not information in the CAD model in its native definition to specify which surface is more important for the quality. That's something that you might get into later with product manufacturing information, which traditional manufacturing in CAM can take advantage of, but we're not seeing that yet in 3D printing. But that's certainly possible with the spatial components, that you could import that product manufacturing information and use surface finish tolerances as an input to optimizing the orientation. And then if you're going to make multiple copies of this part, or you're going to print different parts together in the same job for time management purposes, you need to arrange all these things into your build volume. That's something that's much easier done when you have a 3D environment that you can move parts around and see easily, rather than just the limited 2D representations that I've seen on some of the machine softwares available today. The wide world of support generation. You know, most of these parts aren't able to be printed just as they are. They require some additional material to hold up those overhanging surfaces. Now, exactly how much of those support is needed varies wildly by the process that you're using, the material that you're using, the surface finish requirements of the part, the shape requirements of the part. There's so many variables here to be optimized. But the actual process then of creating the supports can be varied a lot. You have different geometries that are preferred for different materials. Different users will develop a favorite, right? They like straight column supports, or tree-shaped supports, or solid supports, or hollow supports. So many possibilities. The important thing here is that if you have a strong 3D modeling engine available to you, then this application can make supports as complex or as automated as you want to offer to the user. In this case, for this picture, I've designed something that, you know, is fairly simple, a cross shape, a T shape of the support with a conical contacts to the part to minimize the amount of surface area it's touching the part, so they'll break off easily and sand up nicely. But the flexibility of having a fully capable 3D modeling engine really opens up the world of what you can offer in the application for support generation. Now finally, you've got all the geometry you think that's ready to print. So it has to be sliced. Slicing seems pretty simple, but often the results have to be validated. They might need to be modified or healed if you just find sections that are too thin, you know, the wall thickness is too thin, or other things that are not compatible with the process that's going to be used in the printing. Spatial components have a unique advantage in that we can slice both precise BREP CAD geometry and tessellated geometry like comes from STL, and we can do them all together. So because we have the power of our modeling engines that are designed for precise BREP or for polygonal STL-like data, we can offer up this flexibility to do both very easily. Then it comes to instructing the machine. What's the machine need to do? The path creation. This is something that is maybe doable in the simple 2.5D world of planar machines like powder bed or FDM. Although there are still some complexities to get better results, right? Again, dealing with what's up-facing surfaces versus down-facing surfaces. You may have different machine parameters. You also may treat support geometry differently from the part geometry, have different machine parameters that control the material density, the infill patterns, etc. Then we get into the world of 5-axis additive, as we see in directed energy deposition or laser cladding, sometimes called. Now we're talking about full 5-axis CNC path control. And there are very few companies to do that well. We're partnered with the industry leader to provide that capability so that no matter how complex or capable your machine is, Spatial's platform will be able to provide the tools to do the path generation. Now let's talk about simulation. We've done all this preparation of the build, right? You've prepared, you've imported data, you've healed it to make sure it's of high enough quality to manufacture, you've oriented it in the volume, you've added the necessary support geometry, you've sliced it, you've got the path. Is it going to work? Is it going to create the part that you want? I'd like to step into a quick poll here again and ask, how many of you are using physics-based simulation to pre-validate the builds now? Jim, would you take this?
Absolutely, Ray. So our question is a simple yes/no. Do you use physics simulation to pre-validate your builds now? It's a simple yes/no question. The results are coming in, streaming in quickly now. Again, the question, simple yes or no. Do you use physics simulation to pre-validate builds now? Simple yes or no. And answers are streaming in as we speak. The poll is still open. And here are the results. 73% report no, they're not using physics simulation to pre-validate the builds. 27% say yes. Ray, I'm a little surprised that 27% in some ways is as high as it is. What's your take on this?
I agree with you, Jim. I am also surprised that it's that high. I think this is a very exciting area, actually. I think this is, as I survey all the software technology involved in additive manufacturing, my personal opinion is that the simulation is the area that's going to change the industry the most in terms of getting it ready for real production applications and being able to manufacture parts using these technologies with the same kind of expectations that computer-aided manufacturing with other technologies has achieved over the last decades. And I'm also excited to see that there's a tremendous amount of new simulation capability coming to the market. Much has come out this year. There's much more coming in the next couple of quarters. So that by this time next year, the tools available to end users to be able to pre-validate and do very highly detailed simulations of their 3D printing process are really going to change the game. And I think this is a critical piece to include in the end user application. Not necessarily all the simulations that are available, because some of them will be better tailored to the metallurgists and the process development folks who are really focused on the fine details of things, or in how to improve their machines to make them more consistent, more repeatable with powder fill simulation and void and porosity creation and such. But the basic question of, is my part going to come out like I think it will or like I need it to? Is it going to have the right basic shape? Is it going to have any major residual stress concentrations? Is it going to have any major porosity problems because of the shape? Because the shape I've defined is maybe not compatible with the process that I've said I'm going to use. Putting that kind of simulation in the hands of the manufacturer, the person who has a machine and needs to make some parts for the first time, that's going to really change the game. It's going to reduce the number of reprints, the number of failed prints. It's going to make those people much more efficient. You know, manufacturing time is not just about the money spent on raw materials. It's about the lead time, right? How quickly can you complete the job and move it on to the next step? Those are really high value areas that you need to save people time and make it reliable. And that's going to turn into real value for those software applications that can deliver that. So once you've done the simulation, finally we're ready to go and make the build, make the print, if you will. And if we've done all of these steps of preparing the data well and preparing the manufacturing well and simulating in advance, then this hopefully will evolve from being a cross your fingers and push the button step to knowing what's going to come out and move on to the other thing on your desk, the next job in your queue that you need to work on. So our audience members who are working with 3D printers or even doing research in this area, working with different printing technologies, I suspect are familiar with the fact that many of these jobs have to be done in completely separate applications today. I've interviewed end users in my local area who are making parts, and they have to use 5 or 6 different applications. And in one case I saw, they had 3 different applications from the same vendor that were not integrated, plus the other applications from different vendors. Made it a very awkward flow, and it's not one that, it's just not efficient. There's a lot of room for improvement. In fact, I'd like to conduct one final poll of the audience here.
All right, thanks, Ray. And audience poll is a choice of 5 options here, and a very simple question. That is, how many different applications do you use in your workflow? Please select one of 1, 2, 3, 4, or 5 or more. It's a simple question of how many different applications do you use in your workflow? Choices from 1 to 5 or more. And voting, the actual results are streaming even faster for this poll. That's good news. And results may surprise in this case, and they're still pouring in. Number of applications, of course, it's essential to your thesis, Ray, of are we using too many, and what does that do to productivity and risk, design risk? So how many different applications do you use in your workflow? 1, 2, 3, 4, or 5 or more? And here are our results. Our results, it's a fairly even spread. 1, not surprisingly, 23%, 3 at 37%, 5 or more, 7%, and 4 at 13%. Those numbers strike me as a little surprising. They look high to me, Ray. What do you think?
You know, I think it's a strong validation of the thesis, as you said. You know, the largest response was people using 3 applications. And if we couple that with the fact that the majority of respondents to the prior poll we're not even doing any kind of physics-based simulation yet, I think it tells us that to make the user able to take a part and get it to manufacturing with high confidence that it's going to produce the part that they need to make, they need to be using 3 or 4 more applications today. And I'll bet none of them really like that. So that's why Spatial is bringing the solution. The solution is the additive manufacturing platform to enable original equipment manufacturers or software ISVs to deliver one unified application, to enable end users to do the whole job in one software application. You know, the last person that I interviewed last week, he said he uses a a very well-known mechanical CAD system to do all his translations. Then he moved those into a very well-known CAM system to do his modeling because that's what he was comfortable in, and convert that to STL. And then he uses a very well-known additive manufacturing application that works on the STL and generates support geometry and does slicing, and then send that into the proprietary software from the machine manufacturer to do the path generation and the nesting and patterning. So they're without any simulation and without even optimizing the build path to his own liking. He's using 4 separate applications. So we really think that the value to bring to the market, the next evolution that really will mature this additive manufacturing market to be on a par with the other manufacturing technologies we're all used to, is for the OEMs or ISVs to step in and deliver a unifying applications to really serve the user in this way. And there's an important business argument to be made for this. You know, if you're a machine manufacturer and you're selling a printer, but you're not delivering a software solution, or your software solution is hodgepodge, you're really leaving yourself in a competitive a disadvantage against a competitor who has a better software solution. In fact, you might be losing out on hardware sales because you're not offering a more complete solution that's more attractive to the user. Compared to the machine manufacturer who's going to control the entire software solution, they can maximize not just the software revenue that they get, that they were leaving on the table before, but maximize the hardware revenue because they have competitive advantages by delivering a complete solution that's easier to use and more reliable to use for the end user. They're going to get maximum revenue and margin and make users happier in the process. So while most of our audience attendees we found in the first poll are more of the end user variety, I suspect they would be happy to have a single application that works well with their machines that they're able to use and know that they can reliably manufacture parts that they're given. So that's our value proposition to the market, that Spatial is here to change additive manufacturing, bring this market forward, and make it easier for people to use additive manufacturing technologies in a production environment. So now, Jim, I'd like to open it up for questions from the audience.
Thanks, Ray. And just a reminder to attendees that there's a console in front of you on your screen, and I encourage you to go ahead and key in a question. As those questions pop up, I will present them to Ray on your behalf. And let's kick off right away. Ray, do you have to create and manage a CAD plugin for every CAD vendor that I want to be compatible with?
No, you certainly don't. That's a strength of Spatial 3D Interop product line, is that we provide the technology to directly read the native CAD files from all the leading mechanical design applications, the ones that are developed by our parent Dassault Systems and the others on the market. We enable downstream applications to read 3D data with the most reliable translators available on the market. And that's something we've been doing for more than 15 years, so we really are the market leader in that technology.
And Ray, could you comment, expand a little bit on how you manage slicing CAD and the STL files?
Sure. So Spatial has been known historically as a leader in providing precise modeling kernels like ASIS and CGM, and that gives us the power to do all kinds of geometric operations on precise CAD data. But we also have a more recently introduced technology called CGM Polyhedra, which is a modeling kernel written specifically to work with tessellated or polygonal data like we see coming in from STL data. So with those two things together, we have merged them together to do what we call hybrid modeling. So they can work in the same model space. You can have bodies that are precise from a nice mechanical CAD system or created natively in CGM. And you can have data that's polygonal that was imported from STL. and those things can live in the same space and interact and model on both types of data at the same time. That's a power that Spatial brings with all of our modeling expertise that is unique in the industry.
Ray, when I look at some of the examples that you presented in those slides, it looks like we're moving to a world where you have to visualize your part basically as a collection of surfaces that have multiple polygons, essentially simple geometric shapes, which are infinitely small to create a sort of a smooth, usable surface at the same time. Now, what I'm wondering is that if we have that kind of power, they're able to do that. Is it designers or users, can they determine exactly what surface finish, if you will, or what level of fineness that they need for the given part, and can they bump up against the limits of the machine, and is there sort of a trade-off there?
That's a great question to help me explain some concepts and the importance or the relative value of having precise CAD data versus the tessellated data. So most everything that's designed in the manufacturing world is designed in a precise CAD system, and they have near infinite precision about capability to make smooth surfaces. But if that data has been tessellated and saved as an STL file, you do that with, it's an approximation, right? All those triangles you see are an approximation of the true cylinder or sphere or curved spline surface that was the native definition. And the accuracy of that approximation, once you've written that into an STL file, that accuracy is fixed and you can never make it better. So that's why we strongly advocate that people use the precise CAD data wherever possible, because then you have the power to control the accuracy of that approximation before it gets sent off to the machine that's going to do the manufacturing. And some machines, in fact, have very higher precision capabilities in their manufacturing. And I've talked with some customers using our components who actually are going to do all their slicing and path creation from precise CAD data and not ever go through the tessellation step to approximate the data.
Yeah, right, that's interesting. That's certainly a high degree of confidence if you can do that. From those who are coming from the subtractive, say the 5-axis machining world, you still think in terms of tolerances, but the general assumption was that if you're going to G-code, if you could get as much as an order of magnitude, more precise at the design level, then essentially any tolerances or error at the design level just disappear into the G-code, if you will, and that you're so much better than the machine's capability. I'm just wondering in this case is that if we're at a point now where we can design so much better than the machine can produce, should a designer perhaps design less or worry less about precision repeatability given the capability of their machine? Does that make any sense?
I don't think that they should, and I'll tell you the chief reason why it gets introduced in the world of translation. So, each mechanical modeler has a definition of its core resolution, right? How close can 2 points be and still think that they're separate versus when do they just merge together in numerical noise? But as you translate data from one system to another, right, from CATIA to STEP or CATIA to NX or something like that, each system has a different tolerance and a different even scheme of how they use those tolerances. So I always think it's best to maintain the highest precision of the data for as long as you can, because you're not going to give up that accuracy until the last possible moment. And the manufacturing processes vary so much, the designer may not know exactly what's going to happen. As I said, I've worked with some 3D printer manufacturers working on what they consider a new and innovative printing technology that are working at such a fine resolution that they didn't feel they could accept the approximation error created by tessellating the part. And so they're building their paths directly off the very precise spline data from the CAD model. So I'll repeat, we want to preserve as much accuracy of the data and high fidelity as we can for as long as we can. and not approximate until you absolutely have to.
Well, that makes sense. It sounds like 3D printing is better than perhaps we think it is now, and it's getting better in a hurry.
Oh, absolutely. You know, I think if you're one who reads the press regularly, it seems like every month, maybe even every week, someone announces that they've got a new printing technology. And you know, we had a lot of attendees today coming from academia, and I'll bet a lot of them are involved in trying to develop new manufacturing technologies that are either faster or higher precision. So this is a really exciting field that's just exploding in technology.
Yeah. Ray, what's the skill level required to work with your Spatials application? Is there a ballpark how many hours of training is required to become proficient? Is it as complicated, say, as a native CAD apps?
So something I guess we should have explained earlier is Spatial doesn't make applications for end users. Spatial makes technology for other people to build applications. So we only work providing technology to the big name application developers that you probably know, right? Companies like SolidWorks and Mastercam and those names. Those are the applications who use technology from us. So we're setting out here to change the additive manufacturing landscape to enable those companies who make machines, like some of our customers like Renishaw or SLM Solutions, to build more comprehensive application that's easier for the user. So I'm dodging the question a little bit because we don't actually make an application. So how complex the application is and how easy it is to use is something that's controlled by the application developer. And we provide lots of technology that gives them options to make things more complex with lots of options and lots of user interaction, or they can go the other way and make things simpler with more automation and more assumptions. And that's the fun part of the market, is that we get to see how our customers choose to solve the same problem in different ways.
Ray, a more technical question this way. Is your UV rendering auto or manual? And just for those who aren't familiar with it, UV mapping, that's a 3D modeling process where you sort of project a 2D image to a 3D model surface for texture mapping.
So we do have some tools in our modeling engine to map 2D data onto a 3D surface. That's mostly for real geometry applications and not so much for texture mapping or putting an image onto a part. Our strength is more in creating geometry, like if you think of a flexible antenna that needs to be wrapped onto a 3D surface in an electromagnetic kind of product manufacturing application.
Ray, when it comes to actually making parts from designs, historically it essentially took two people, a designer and a machinist, a design engineer and a manufacturing engineer, someone that could design the part and someone that could program the G-code. Can machine toolpaths can they be created from CAD with limited user input? In other words, can one person do it all?
They certainly can. And it really comes down to how much control, how many variables do you want to modify. But in the simple flow, you can take a CAD model and directly turn that into G-code with zero user interaction. Now, if you ask a manufacturing guy, he'd probably say you're crazy, because the manufacturing guy has all that expertise about, oh, but I need to change feeds and speeds here to get a slightly different result, right? But it's certainly possible to do that. We have the tools in these components of it possible today to go directly from CAD to G-code with no interaction. And that's a pretty exciting development, because we actually are hearing more and more from our customers in the manufacturing space, the machine tool manufacturers, that the population of knowledgeable machine operators is dwindling, and they're finding it very hard to replace. So they're seeing the need to really increase the automation of software to account for the fact that they can get fewer and fewer skilled machinists. And the same, I think, will be true in 3D printing, right? People don't want to develop the very detailed knowledge about the process parameters that can be varied, right? Laser strength and spot size and scan speeds and all that. They really want to be able to just print that part. And software is going to be the way to do that.
Ray, you mentioned those manufacturing engineering types who'd say you're crazy. Well, I used to be one of them. However, I'm seeing some progress in 3D printing now that's fairly boggles the mind. There's a very large Palo Alto, California-based manufacturer of 3D print technology, who shall remain Hewlett-Packard, that have an interesting new technology, for example, that it does it differently. You have multiple ways to 3D print parts now. I mean, there's laser sintering, there's some liquid UV catalyzed processes still out there. I mean, there are HP is a new thermal process at this point. Should that platform change the way they approach the design function, or do you go ahead and design the part and then not worry about the actual methodology for forming it?
Well, very interesting. You know, I actually have a split opinion on that. You know, sometimes I think you're designing, the part should be functionally designed. As an engineer who thinks everything's functional, I don't really care what it looks like. I think parts should be functionally designed, and then you figure out what's the best way to manufacture that part. But there's certainly a growing need for education in design for additive manufacturing. And I'm actually pretty excited to be sitting in on a course next week on that very topic to see how it's being taught and how people are interested in the topic. Because just as we taught design for manufacturability starting in the 80s and 90s to mechanical engineers, that helped us be better engineers, right? And make parts that could be manufactured cheaper to still achieve the same goal, right? Or maybe can be designed to be lighter so that your end product is more efficient. Those same principles are going to apply in additive manufacturing, but the tools are different, right? Because the manufacturing processes can create so much wildly different things now than they could before. And as you described, all these new, the new printing technologies are coming out so quickly that I do believe that the concept of design for additive manufacturing is very immature and is going to be changing a lot in the next several years.
Ray, if you're used to designing for, say, 5-axis machining, you mentioned you can generate code directly from software at this point. Is there going to be a comfort level of going directly to code from this point, or do you think that at least initial stages, designers are going to want to either get their hands on the coding directly or pass it off to a manufacturing engineer and say, look at this?
I think it depends a little bit on the process. I think if you're creating a part from scratch, I think automation can go the whole way, or at least very close to it. If you look at some of the hybrid machines that are being used for part repair, where you're going to, they start with a physical part that already exists, and you got to go and add material to it and do some finished machining on that. Boy, I have a hard time seeing that being fully automated. Examples that some of you have probably seen, like, we've got a turbine blade that is cracked or has a chip in it, and that thing needs to be put into a machine, new metal welded onto it, and then finished machined to get it back into spec for the shape requirements. Anytime you're dealing with the built world, there's variability on those parts, and that's going to take some hand-holding, some manual intervention to make sure that process comes out cleanly.
Ray, it's funny you mentioned that, because in terms of the hybrid machines, of course, naturally, the vendors of hybrid machines tend to be 5-axis subtractive machining center builders. G&G Morikiki, for example, one of several that have an expensive and highly capable machine. And many I talk to in the industry say that they feel that it's early and that the focus is still on, as you say, repair of broken components, which really is sort of like a very sophisticated way of, plasma spraying crankshafts, the way it's been done for the last 30 years. Do you think, it seems to me that the field is wide open for designing for hybrid processes, but if you do, you've got to talk about creating G-code for cutting material, but then also code for additively adding material, and perhaps another layer of G-code for machining back the material that you've added. How much complication does that add?
It does quite a bit, but our partner ModulWorks is already delivering the tools to handle those kind of multi-stage, multi-technology manufacturing processes. So in fact, you know, we can do that where we can split the part, say, okay, print this part, now then go and machine some of the features that you've just printed, then go back and print some more. So the capability is there. Now that's not, I don't think, something we're ready to say is fully automated. You're still going to require some user input to drive that process to specify where do you want to break up the process between add and subtract and add and subtract. But the automated toolpath generation for each step is there and available. And of course, you couple that with a driver specific to the machine so that you get good G code for that machine and just not something generic. Then we're ready to enable those machines today.
And Ray, the simulation. Yeah, the simulation's gone from sort of a laboratory of curiosity to something that I have used in the past just to validate, you know, physical testing to a point where we're using it now as part of the iterative design process. Question about the simulation is that in terms of 3D printing, can we simulate close to what we're going to get with the final part, or to what extent we still have to run it on the machine to be certain that we're going to get what we want? The physics, I mean, the mechanical aspect of 3D printing is still, in some ways, an imperfect art.
Yes. I'm really impressed with what the simulation is capable to do today and what's coming out in the next few quarters. I've talked to most of the big players in simulation just in the last couple of months about what they're offering in additive manufacturing. You know, what kind of simulation tools do they have targeted specifically at additive manufacturing? And I was really impressed with what's available and what's coming out soon. As I mentioned before, from simulations all the way down to the micrograin structure forming in metals from the welding process, up to, you know, gross deformation of the parts due to the residual stress and the sequence of operations that'll build that part. So I really do think there's great capability. It is a bit early. You know, these are new simulation tools, and I'm sure they're based on sound math and physics fundamentals, but it'll probably take a little while for people to get good at using them, become efficient at using them. But I do think that the simulation tools available will allow people to pretty accurately predict what they're going to produce. Now, will people take the time to use them? That's another question.
Ray, it's an interesting point. Those of us involved in sort of hard part manufacturing, aerospace, automotive, appliance, my background's automotive, the customers always loved functional prototypes. They'd love you to send over 1 or 2 or 10 of the part that you plan to build so they can sort of roll them over in their hands and pass them around at engineering meetings, this kind of thing. And one of the promises of 3D printing, of course, is you could reduce the sort of the time to market by taking some of that prototyping time out of the equation. It's a lot faster and easier to do. Some are reporting back to me that in some ways 3D printing actually has exacerbated that problem, of course, by making it easier for the customer to demand more and more samples, functional prototypes, almost pilot runs of products to fool around with, and they're not seeing the sort of shortened development time that they promised. Does simulation look like the final solution of that problem? Are we going to reach a point where the simulation is so good, it's so accurate, that the customer will accept the simulation as the final evidence and just give a go-to production from there?
Well, I suppose it depends on the customer, but I think what you described was more about human emotion than people liking having a thing in their hands. And no matter how good the picture is on the screen, it's just not quite the same as having a thing in your hand. So I suspect there's still going to be an enduring demand for physical prototypes because people just like them.
Yeah, that makes sense. Ray, we talked about support structures, and it's at least the more I learn about 3D printing, the more I realize that how you support the part really is, in a lot of ways, the most critical part of the 3D printing process. Some 3D printer manufacturers now, of course, are going to 2-component systems. We'll talk about plastics, of course, now, with, of course, a dissolvable support structure that reduces some of the cost and time, of course, of finishing the part afterwards. Does that sort of 2-component thing, does that alter or change the way you use the software?
No, not at all. I mean, I would would consider that a basic 3D modeling concept, that you got separate volumes and different materials. That's not a tricky part at all from the modeling standpoint.
Yeah, we talked about, we saw in the poll a surprising number of users using multiple platforms. By multiple, I mean 3 or more platforms, which strikes me as that would naturally be a red flag for any engineering manager anywhere. If it's possible to reduce that to one unified platform at that, but I can see some cost benefits at the back end. Is this something you'd expect engineering managers to chase at their end, or would there be some demand push from the bottom end? Could designers you could see at the board level call up and say, look, we need to clean this up because this is taking too long?
I certainly think that there will be grassroots support for this, because just think of the training requirements to learn and get proficient in 3 different design and manufacturing applications, and then add on a simulation application to that. So now we're at 4. Maybe we get something else. So 4 completely different user interfaces. Those applications are updating with new revisions and completely different schedules. From a user management standpoint, from the guy who actually has to go from desk to desk and application to application, the ones I've talked to don't like it. And I think they would really welcome having a single application to work in.
Yeah, Ray, we're nearly bumping up against the hard stop at the top of the hour. I think we're going to have time perhaps for one more question. And that question is that the retraining function. Are you better off with an integrated platform like yours, starting with someone essentially fresh out of training and new to modern CAD CAM and simulation systems, or can you retrain someone who's using this existing multi-platform system? Can you teach an old dog new tricks in this?
Sure. I have every confidence that the people working in manufacturing to advance their manufacturing technologies, moving from 3-axis mills to 5-axis mills, now adding additive and hybrid machines, I have every confidence that they can take on these new technologies and the software tools that are well designed to support those technologies. I haven't talked to anyone in my travels, and I've been out, interviewing end users for quite a lot of this year to make sure that we're delivering the right technologies that people really need. And I haven't talked to any of them that are scared away or scared off by the thought of needing a new software application to be able to use this $1 million machine that they just put on the floor. What they are worried about is how can they do it efficiently, and how can they get reliable output from that $1 million machine.
Well, Ray, that's a great summary statement. I see by the clock on the wall we're bumping up against our hard stop at the top of the hour. I'd like to thank Ray Bagley, Product Management Director at Spatial Corporation, also Spatial Corporation themselves, for sponsorship of today's webinar. And just a reminder to all attendees that this and all past webinars will be available for viewing again on www.engineering.com. Thanks and goodbye.